Alrighty. So the bell work says the function f is defined by the equation above, which is f of x is equal to 2 to the x plus 1, which is the following graph. Which of the following is the graph of y, which is a negative f of x in the xy plane? So first thing we got to realize, and I know we haven't covered this just quite yet, we're going to cover it in the next section, is when you have the situation where you have a negative f of x, this negative corresponds to a flip over the x-axis, or reflection over the x-axis. It's basically the same thing as when you're dealing with a parabola. If you have a negative a value, instead of a parabola opening upwards, it's opening downwards. So without knowing a whole lot about exponential functions, we can actually make a pretty good guess of which graph it is. So, and the way that we're going to do this is we're going to find what's known as the y-intercept, or f of 0. So f of 0 is going to be equal to 2 to the 0 power plus 1. Anything to the 0 power, whether it be a binomial, it could be a million, it could be a billion, any number that is to the 0 power is going to be equal to 1. So f of 0 is equal to 2, okay, or the point 0.02. Since we have this reflection over the x-axis, that's going to take our y value from being positive to a negative. So a negative f of x, or f of 0, to the 0 plus 1, is going to be a negative 2, or the point 0, negative 2. Okay, so without knowing anything about exponential functions, we want to find the graph that has the point 0, negative 2 listed. The graphs that they give you on the SAT, they're not always great. You can see letter A, it crosses at 0.2, so that would be more of a reflection of the original graph. Graph B has 0, negative 1. Graph C has 0, negative 2, so that's a front runner. And then D has 0, negative 1. Since we were looking for the point 0, negative 2, the correct answer to the bell work is going to be letter C here. Okay, and like I said, we're going to be covering transformations and graphing special functions a little bit later on, but these questions, they come straight from so the SAT, Shylin, is going to be tackled in the spring semester. Since so much is still up in the air, I imagine that you guys will still come in because we have to like standardize the process. Like I have to go to a training just to proctor the SAT. So I imagine that they're going to bring you in, but I would just wait for communication from the school on that. I can't really speak to that, but I would imagine that you guys would be coming in. Okay, this, like I said, it comes from the SAT with no calculator, so there's no reason to plug it in to a calculator. If we're able to find the y-intercept and knowing that anything to the 0 power is equal to 1, 1 plus 1 is 2, and then knowing the reflection, it's a pretty simple problem. We're just looking for a point 0, negative 2. That brings us to our lecture. If I open that up, minimize that, share my screen. All right, so first thing we have is our 5-minute check. It's going to refresh section 2.2. Number 1, it says state whether f of x, which is equal to 2 plus x squared, is linear. Okay, part of the requirements of being a linear function is that our x variable is always to the first power. So that's kind of a tip. Also, if you know anything about what the graph of x squared is going to look like, it's going to look like a parabola. So it's going to be a U-shape or nonlinear. So for this question, yeah, that's fine. So for this question, letter B is going to be the correct answer. It's not a linear function because x is raised to the power of 2. Okay, the next one. State whether x minus y is equal to a negative 6 is linear. Okay, so with this question, we have x minus y, which is equal to a negative 6. And the main way that we express linear functions is to try to get it into the form y equals mx plus b, or we want to be able to solve for y. So if we isolate the y variable by subtracting x from both sides, we have a negative y is equal to a negative x minus 6. Okay, and then we have to divide, because there's a coefficient of negative 1, we have to divide each side by a negative 1, which shows that this is y is equal to x plus 6. Does this fit the form of y equals mx plus b? Yes, it does. M is equal to 1, b is equal to 6. Since it can fit that form, our exponents or our x variable isn't raised to another power, we can conclude that this is a linear function. So the correct answer is going to be A, yes. Okay, awesome. All right, looking at number 3, it says, does the graph have line symmetry or point symmetry? If so, identify the line of symmetry or the point of symmetry. So, key thing to remember is that line symmetry what we do is we draw a vertical line that divides the graph into a left half and a right half. If the function has line symmetry, when we fold it upon itself, so kind of like how you'd fold a piece of paper burrito style, you know, you have your line here and we're going to bring this side over or this side over, our graph maps upon itself. So line symmetry is all about drawing a vertical line and then folding it upon itself. Point symmetry makes 180-degree rotation about a point. Okay, so for this graph, looks something like this. What it means to make a 180-degree rotation is if we were to bring this down here, would it map on top of itself? Okay, so looking at the graph on the slide, we can clearly see that this isn't going to be line symmetry. Because if we divide it, say, upon the y-axis, this portion that's in quadrant 1 is going to map onto quadrant 2, whereas this portion that's in quadrant 3 is going to map onto quadrant 4. So we can't really find a point or a line that we could flip it over upon itself that would show line symmetry or where the graph maps upon itself. So answers A and B are completely off the table. But if we look, we have point symmetry here about 0, 2. So 0, 2 is this point, okay? And remember, when we're looking for point symmetry, we want to count how many movements we make to the right and how many movements we make up. So we go from 0, 2. If we go 1 right and 1 up, you can see that we fall upon the graph. From 0, 2, if we go 1 left and 1 down, we also fall upon the graph. That's indicative of having point symmetry. So if we were to rotate this graph about this point, this would fall upon this graph, even though this section is a little bit longer. Okay, because this would continue upon the same trend. So this graph does have point symmetry about the point 0, 2. Number 4, does the graph have line symmetry or point symmetry? If so, identify the line of symmetry or the point of symmetry. So here we can eliminate an answer pretty quickly. Answer choice C is not going to be correct because what it's saying is that if we were to rotate it about the point -3, 1, 2, 3, 4, all the way up here, would that graph map upon itself? So 180 degrees is like walking in a straight line and then turning exactly around and then walking back down that same line. Okay, you hear it a lot when you're talking about action sports like skateboarding, BMX, snowboarding, that type of stuff. 180s, if you're a skateboarder and you're riding with your left foot forward, if you do a 180, you're going to end up where your right foot's forward. So it's an exact flip. If we were to flip it about this point, this area would come up to the top and then our ends would be pointing down. It doesn't map upon itself. So we can't have point symmetry here. So this one, it is line symmetry, but we have to pay attention to where it says line symmetry and about. So we're looking for the line of symmetry, which is indicative or is given to you by x equals -3. We also have line symmetry at -3, 0. Okay, -3, 0 is a point. X equaling -3 is a true line. Okay, it's not a function, but it's a true line. So if we look about -3, if we were to fold it over, if we go 1 to the right and 1 up, we hit -2, -3. And then if we go to the left, we're at -4, -3 here. That's showing that we have line symmetry about the line -3. This is the dividing point. It gives us a left half and it gives us a right half. We take this right half and fold it over, it's going to map exactly onto the left half. So our answer choice that fits best is answer choice A. It can't be answer choice B because that's about a point, and it can't be point symmetry because if we rotate the graph 180 degrees, we don't map upon itself. So the correct answer is A, line symmetry about x equals -3. Okay, so what we have on tap today, we're going to identify end behavior of graphs and identify extrema of functions. Okay, and there's two ways to think about this and two proper ways. So when you're dealing with end behavior, we have our x and y plane here. We always want to start at the origin and we want to work to the left to where we're going to have x approaching a -infinity. Okay, how far can we go to the left? We can go to a -infinity. So what is this graph doing as we move farther and farther left? And then on this side, once again, we want to start at the middle and work to the right, whereas x is approaching a positive infinity. Once again, infinity being the greatest number that we can imagine. Okay, this requires you to have a lot of trust in what you're seeing. It's not a very hard concept, but it's kind of hard to wrap your head around if you can't see the concept. We have to have faith that they've shown everything that we need to know in the picture given. Okay, and we're going to express our answers as x goes towards a -infinity and as x goes towards a positive infinity. And then what is our graph doing? Okay, so that's the method of thinking that we have to have when we're talking about end behavior. When we're talking about extrema, okay, extrema are turning points. They happen when the graph comes from increasing to decreasing or decreasing it'd help if I could spell to increasing. Okay, and what we have to remember is when we're talking about increasing and decreasing, we're talking about the y values. Okay, and the way that we find extrema is if I just draw a sample graph here, say it's a parabola. We want to look at it as going left to right. So as I come from this side and I go to the right, you can see that my y values are decreasing. They're going down. They keep getting less and less and less until I hit this extrema point, right? My extrema point's right here on the y-axis. Then as I come from this point going to the right further, I start to increase back in y values. Okay, this point is an extrema, and it's where my graph has stopped decreasing and has begun to increase. This sets up what's known as a relative min or relative maximum value. Okay, and these are going to be graph specific. This in this case would be a relative min because this is the lowest point on the graph compared to everything around it. Okay, if it was a parabola that shaped something like this, then this point would be a relative maximum. It's the highest point on the graph, or it's the lowest point on the graph. Okay, but the way we find them is we work left to right and we try to determine what our graph is doing. It's decreasing, 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 and then it begins to increase. And then once again, the decreasing or increasing is in terms of the y values. So here I'll just put in a sample. If that's 10, that's 5, that's 0, that's negative 5. You can see I started at 10, and then I went to 5, then I went to 0, then I went to negative 5, then I went back up to 0, then I went back up to 5, back up to 10. Okay, so I was decreasing, decreasing, decreasing. I hit a point, and then I began to increase again. Okay, this point, the lowest point, or where it begins to turn, is known as an extrema point. Okay, your extrema will either be a relative min or relative max. Okay, but it's all centered around the y values. So on in behavior, we want to start in the middle, work to the left, and work to the right. When we're talking about identifying extrema, we want to know, what is our graph doing? Is it decreasing and then increasing? Is it increasing and then decreasing? And that allows you to find those points, those maximum or minimum points, is what we're going to be talking about today. So here's your new vocabulary. We have end behavior, relative maximum, relative minimum, turning points, and extrema. So extrema are turning points where the graph stops decreasing and begins to increase, or it stops increasing and begins to decrease. Your extrema points also turn into a relative maximum or a relative minimum, depending upon the graph. And then in behavior is all about what is our graph doing as x goes towards a negative infinity and a positive infinity. Okay, so we're looking at the very, very far out pieces of our graph. But we always start at the origin and we work out. Okay, when it comes to in behavior, when you're trying to identify extrema, we start from the left and we work to the right. Okay, so here, describe the end behavior of each linear function. Okay, linear functions, they're pretty simple when it comes to end behavior. 90% of the time, you're going to have one end that approaches negative infinity and then one end that approaches positive infinity. And that's talking about the y values. You can see on our graph here, it starts low and it ends high. So if we start at the origin, which is at the O right here, and we work farther and farther left, you can see that our graph continues to go farther and farther down. This is where we have to have trust that they've shown us everything that's important on the graph. Okay, we have to assume that there is no turning point outside of what is shown. So the farther and farther we go left on this graph, our function continues to go farther and farther down. So we would express that as x goes towards a negative infinity, y goes towards negative infinity. Okay, and that's because there's no stopping points. Okay, and this is the left-hand side. Okay, there's no stopping points on the graph. It has arrows. We have to assume that is as low of a value as we can think about in x, our y value is going to just keep decreasing and decreasing. This negative infinity and negative infinity, you're going to see that a lot. Okay, and just remember that infinity, if it's a negative, it's the lowest possible number that you can imagine. Okay, but now let's look at the right side, because there's two ends to every graph. You have a left-hand side, you have a right-hand side. So starting at the origin again, it's kind of cut off because our graph is shifted to the left. But the farther and farther we go right, you can see that our graph has an arrow that shows that it goes farther and farther up, or it increases in value. Okay, what this means is that as x goes towards a positive infinity, y goes towards a positive infinity. Okay, and that's just because the farther and farther we get over here, our graph just continues to go up and up and up. Okay, it has a positive slope. A slope will tell you a lot about this. So positive slope, meaning that the farther we go to the right, the higher our graph is going to rise. Therefore, we can conclude that as x goes towards a positive infinity, y goes towards a positive infinity. So this would be your left end behavior on top. And this would be your right end behavior. Okay, so as x goes towards a negative infinity, so the farther we go left, the graph goes farther and farther down. And the farther we go right, the graph goes farther and farther up. Okay. So as x goes towards positive infinity, f of x goes towards positive infinity. They use function notation. I abbreviated with it with a y. That's going to be fine. You would want to express your answers in function notation. I just use y because I omitted it. So as the value of x approaches positive infinity, the value of y will continue to increase and the graph will continue to increase and approach positive infinity. We have to use positive infinities because there is no stopping point. Okay, the graph continues on for eternity. And then, so this is our right-hand behavior. So as x becomes increasingly more positive. So, and then down here is our left-end behavior as x becomes increasingly more negative. So as x goes towards a negative infinity, f of x goes towards a negative infinity. And that's because as the value of x approaches negative infinity, the value of y will continue to decrease. That's where that truss comes in. Okay, if it has a stopping point, if it does not have an arrow, then you don't have end behavior. It has a stopping point. The graph comes to an end. But for everything that is extended on, barring a horizontal line, chances are it's going to approach either negative infinity or positive infinity. And I think our next one is a horizontal line. So that's your answer right there. Okay, looking at this one. This is a horizontal line. Y is equal to negative 1.5. It does not matter what our x value is. We could plug in 1,000, 2,000, 2 million, a billion if we wanted to. We are always going to end with y is equal to negative 1.5. So how does that affect our end behavior? Okay, since we have a y value that does not change, or since this is a linear function with no slope, it's just a horizontal line, our left end behavior and our right end behavior are going to equal the same thing. This is example 2. Okay, so since once again we're dealing with y is equal to negative 1.5, means whatever x value we plug in, we're going to get 1.5. So as x goes towards a negative infinity, is our y value going to change? No, doesn't matter what x value we have, y is always going to be a negative 1.5. So we could say that f of x is equal to a negative 1.5, or y is equal to a negative 1.5. This is your left end behavior. We're talking about the right end. Once again, as x goes towards a positive infinity, f of x is equal to a negative 1.5. And that's for the same reason, because it does not matter what x value we would plug into this equation, our y value is always going to be a negative 1.5. Okay, there's no arrows, there's nothing to assume, because there is no change in slope. It's just a horizontal line where the slope is 0. So as x goes towards a positive infinity, g of x, that was the abbreviation that they used. Once again, it's just function notation for showing y is equal to a negative 1.5. That's because as the value of x approaches a positive infinity, the value of y will continue to be negative 1.5. So again, it didn't matter what we plugged in, we're always going to end up with a negative 1.5. So as x goes towards a negative infinity, g of x is also equal to a negative 1.5 for the same reason. The y value never changed, never had a different slope. Okay, so here we have a nonlinear function. Okay, and once again, we're talking about in behavior. So we want to start in the origin, and we want to see what the graph is doing as we go farther and farther left, and what the graph is doing as we go farther and farther right. So working the left side because it's the easier side. So the farther I move to the left, you can see my graph continues to go farther and farther down. So my left end behavior would be as x goes towards a negative infinity, f of x goes towards a negative infinity. And that's because the farther and farther I go left, the farther and farther my graph decreases. Okay, talking about the right side, starting at the origin. So it kind of throws you for a loop because it has this little extremal point here where we're decreasing, 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 but then our graph begins to increase again. So we're talking about in behavior, so we don't even have to pay attention to that. Okay, this little extremal point doesn't matter to us. The farther we go right, overall, the higher our graph increases. So our right end behavior, as x goes towards a positive infinity, f of x goes towards a positive infinity. Okay, and we would express our answer just like that. This is example 3. And what it's saying on the left end, the farther and farther we go left, the farther and farther our graph goes down, or as x goes towards a negative infinity, f of x goes towards a negative infinity. And then our right end, the farther we go to the right, the higher our graph goes. So as x goes towards a positive infinity, f of x goes towards a positive infinity. Okay, so when you're talking in behavior, it's really just analyzing what the far ends of our graph are doing. We're not overly concerned with turning points. We're not overly concerned with a relative min or a maximum. We're talking about what is it doing when the x value is a negative 1,000 or a positive 1,000. Okay, the farther we go to the right and the farther we go to the left. And like I said, it's all centered around trust, because we have to trust that the graph has shown us all the critical points, that they've shown us everywhere that graph changes direction. And we have to assume that those arrows continue on unchanged until they reach a positive and a negative infinity. Okay. So as x goes towards a positive infinity, f of x goes towards a positive infinity. Layman's terms, the farther we go right, the more and more our graph increases. And as x goes towards a negative infinity, f of x goes towards a negative infinity. Layman's terms again, the farther we go to the left, the farther and farther down our graph goes. But we'd always want to express our answer in something like this format. As x goes towards a positive infinity, you're talking about the right-hand side. As x goes towards a negative infinity, you're talking about the left-hand side of the graph. Okay, here we have a parabola, and we're going to analyze it the same way that we did. We're going to look the farther and farther we go left and the farther and farther we go right. But the key is that with a parabola, the end behavior always end up for parabolas, f of x approaches the same value. So looking at our graph here, it's again starting at the origin. The farther I go left, you can see the graph just decreases more. So as x goes towards a negative infinity, f of x goes towards a negative infinity. Okay, and then as I go farther and farther right, once again, my graph goes towards negative infinity. That's because it's a parabolic shape. You'll find that out later on in pre-calc, that for anything with an even degree, so this would be like x squared, you could add x to the fourth, x to the sixth, the end behavior always approaches the same value. Okay, so if it's a parabola facing down, both ends approach a negative infinity. If it's a parabola facing up, both ends approach a positive infinity. Okay, so we got to determine where those arrows are. So this is the left side. The right side, as x goes towards a positive infinity, f of x goes towards a negative infinity. Show you that. I got to turn the lights on. Hurt my eyes looking at a computer screen in the dark. That's not enough. It's just simply not enough. There we go. Now it actually feels like the sun is shining. Okay. So like I said, with parabolas, in this case, our parabola is facing down. So the left and right end, they both approach a negative infinity. This section here is just describing what end we're working on. So as x goes towards a negative infinity, we're talking about the left side. As x goes towards a positive infinity, we're talking about the right side. Okay, and then f of x is determining what our graph is doing. It's the same reasoning. As x goes farther to the right, the graph goes farther and farther down. As x goes farther to the left, the graph goes farther and farther down. So here would be our answer on this question. All right. Here we get to talk about the extrema of the graph, but they also ask us to estimate the zeros. Okay, whenever they ask you to estimate the zeros, they're talking about x-intercepts. Okay, so zeros equal x-intercepts. Some other words they might throw out is those are equal to the roots of the equation. They might call them real zeros. Okay, but the key thing is we're estimating these. We're not asked to find them, we're asked to estimate. And the key to realize is, or the key that we have to realize is what happens when we cross the x-axis. So if I were to draw just a sample graph here, say it's like a quintic function, something like that. That would roughly be a quintic function, has 4 turning points, it has multiple extrema. So they're asking us to estimate the zeros, which are our x-intercepts. Every time we cross the x-axis, we come from a positive to a negative. Okay, and that's in terms of your y values or your f of x values. Okay, so whenever they're asking you to estimate where a zero is, we want to look at where does the sign change. So once again, we're talking about extrema, so we're going to work left to right. You can see that my y value is positive, and then I hit the x-axis, and then I'm negative, and then I come back up, and I hit positive again, and then I hit negative, then now I'm still negative, and then I hit positive, and then I hit negative again. So if it's given to you in a table, you're looking for sign changes in the f of x value. Okay, sign changes in the f of x value correspond to real zeros, x-intercepts, roots. Okay, and that's because the only way you can come from a positive to a negative y value is because we had to have touched the x-axis. We've had to have crossed it over. Okay, that's the only way we go from positive to negative. So if we're looking at our table, this table is pretty poor. This is a pretty easy question because it gives you where it crosses the x-axis. It gives you 2 x-intercepts here. So estimating the zeros, well, it's pretty easy to find that when the x value is equal to -2, our f of x value is equal to 0. That means we have an x-intercept at -2, 0. Okay, but we also have one at 0, 0. Right there. I pulled up the book. This occurs on page, I believe it's 105, and this is a much better example. Can everybody see the book pages now? Because this is primarily how they're going to be given to you. The problem in the PowerPoint's cake when it comes to estimating zeros. I'm going to just give it a chance to load, making sure that everybody can see what I'm talking about. So like I said, when we're talking about estimating zeros, we want to look for sign changes. So we're given this table. We also have this graph. Okay, so you could use the graph or the table, whichever one fits your bill, but we're centering around x-intercepts. On the graph, you can see we have one between 0 and 1 because it crosses the x-axis. And you can see we have one at 2 because it crosses the x-axis. Okay, on the table, it's a little bit harder to pick up, but we're looking for sign changes and our y value. When does it come from positive to negative and back to positive? So we started out at -2. Our f of x value was 7. -1, 2, 0, 3, 1, -2. That's a sign change. So what that means is that somewhere between the x value 0 and 1, our graph had to have touched the x-axis. It had to have crossed over. Okay, they're not asking us to identify exactly where. They just want us to estimate it. Okay, and that's because of the sign change. And then we go from 1, -2 to 2, -1. So we're still on the negative side of the x-axis. But then once we hit 3, we hit 42. So that's telling us again that somewhere between the x value 2 and 3, we hit the x-axis and a real zero appears. Okay, so on the example in the book, we would list that there's a zero between 0 and 1 and 2 and 3, talking about x values. And we found that because our f of x value changed signs. It went from positive to negative and then negative to positive. And the only way to do that is to touch the x-axis. That's when the y value is equal to 0. Okay, so that's estimating zeros. If I minimize that, we can talk about minima and maxima. These are our extrema points. Okay, so this is where the graph is decreasing and then begins to increase. And what you'll find is that you have a value that's less than the value surrounding it. Once again, in terms of y values, because your x values are pretty consistent. So if we're looking at it, we have -3, 9, and then we have -2, 0. So that means we dropped in 1 point 9 y values, right? We're decreasing. Our graph is going down as we went from left to right. Then from -2, 0, we go to -1, -1. Okay, so we're still decreasing, right? We went from 9 to 0, 0 to -1. Okay, but then once we hit 0, we climb back up. Okay, because we were 0, 0. So what that's saying, I should draw a scatter plot of this. What that's saying and what that's indicative of is that we have a relative minimum at -1. Okay, and I'm just plotting points right now so I can kind of show you a little bit better. 0, 0, 1, -3. That way you guys are able to see it a little bit better. 2, -16, 3, -45. Okay, but you can pick it up from the table, but it's always good to, there's no shame in just graphing it at the same time. So looking at our graph, that's terrible. This point's supposed to be -3. I should have drawn it over there. So we started out at -3, 9. Then we went from 2 to 0, -2, 0, which is right here. And then we hit -1, -1. And then we went 0 to 0. So this point right here is what's known as a relative min. Okay, and that comes from the definition of what's relative. Relative means that you're comparing it to the people or the things around it. We're not saying it's an absolute minimum, like the absolute lowest point on the graph. We're saying in comparison to the points around it, it's less. Because when I was at -2, I was at 0. And when I was at 0, I was at 0. But -1, -1, it's a relative minimum value in comparison on this range from 0 to -3. It's the lowest point. Okay. But then if we look here, we have what's known as a relative max at 0, 0. And that's because when I was 1 point to the left, I was at -1. And then when I was 1 point to the right, I was at -3. Okay, these are our relative mins, these are our relative maxes. This is a graph of the table that was on the slide. Okay, it's much easier to see when you're talking about the graph. But the table is how you really prove it. Okay, how you can prove it algebraically. So once again, that graph is straight from the table. So when I was at -1, my y value or f of x value was at -1. You can see that that is less than the 2 points surrounding it. -1 is less than 0, and -1 is less than 0. Okay, so that shows that -1 is a relative minimum. But then we also identified a relative max at 0, 0. And that's because we have the y value of 0, which is greater than the y value of -1, which is greater than the y value of -3. So of these 3 points, this is the greatest point. Okay, from -1 to 1. This is the greatest point, so that's indicative of a relative max. Once again, our relative minimum that we thought was at -1 is proven because -1 is the lowest value between these 3 points. Okay, relative is we're taking a selection of the graph. We're not saying it's the absolute lowest point because it's not, right? We have a -45 and a -16. We're just comparing it to the points that are around it. Okay, and we're not saying that 0 is the absolute maximum because it's not the highest point on the graph. We have a 9 as an f of x value. We're just saying that next to the points that are surrounding it, it's the highest point in that range. Okay? So they're easier to find when you're dealing with a graph, but the table proves them. That's the key to realize. And they're kind of hard to pick up on a table. It's just knowing that -1 is less than 0 and that 0 is greater than -3. Okay, so you got to have a good number sense when you're dealing with these types of problems, especially if they're given to you in a table format. So we estimated the zeros. We found the extrema. So zeros at -2 and 0. Once again, that was a pretty simple one because our y value was 0, which means that we have the next intercept. Okay, the relative minimum near -1. The relative minimum is the point where the curve on the graph is the lowest. The minimum is at x equals -1. Once again, that comes straight from our table because -1 is less than 0. And then we have a relative maximum near 0. The relative maximum is the point on the graph or where the curve on the graph is the highest in that relative section. Okay, you're not talking about the entire graph. You're talking about that relative section. That's what our graph looks like. Once again, it's much easier to see when you're dealing with graphs. Ideally, this would be over there, but it was presented to us in a table format, so we did the best that we could with the information that we were given. Okay, so here we have a real-world example. So it says the table and the graph represent the balance in Federica's savings account over a year. Use the table and graph to estimate the extrema for this function, then explain the extrema in the context of this situation. So once again, we're looking for extrema, and extrema is the points where our graph is increasing and then begins to decrease, or it's decreasing and then begins to increase. So looking at this graph, I see three extrema points. Okay, and I'm just using the graph here. You can see we're 1, 1100, 2, 1200, 3, 1300, 4, 1300. So we hit a constant area. Then we shoot up to 5, month 5, and we have $1,400 in the savings account. But then month 6, we're back down to 1200. Okay, so this point right here at 5, 1400 would be called a relative maximum because it is higher than the values that are surrounding it. Okay, they're easy to see on the graph, but we prove it using the table. So I see a relative maximum at 5, 1400. Then we decrease to month 6 where we're at 1200, but then we begin to increase again to month 7. So we have back-to-back extrema points. On the table, we go from 5, 1400 to 6, 1200 to 7, 1300. That's a relative minimum at month 6. So I'm saying month 5, relative max. Month 6, relative min. Okay, then we get to month 7, where it's at 1300. Month 8, it increases back up to 1400, but then it drops down to about 900 for month 9. So that means month 8 is a relative max. Okay, and then once again, the table proves it. We started out at month 7, we had $1,300 in the bank. We go another month, we increased our balance by $100, but then we decreased. So we were increasing and then we decreased. Okay, and then once again, we have back-to-back extrema points because month 8, we're at 1,400. Month 9, we're at 900. Month 10, we're at 1,000. So that means that month 9 is also a relative min. Okay, and those are just the things that I picked out by looking at the graph and looking at the table. Month 5 is a relative max because it was higher than month 4 and month 6. Month 6 is a relative min because it was less than month 5 and month 7. Month 8 is a relative max because it was higher than month 7 and month 9. Month 9 is a relative min because it was lower than month 8 and month 10. Okay, they're easy to see on the graph because as we move left to right, we're increasing, hit this point, and then we drop. And then we're dropping, we hit this point, and then we begin to increase again. And we hit this point, and then we decrease again. And then we begin to increase again. So what does this mean in the context of the situation? Well, it's talking about a savings account. So what this represents is she has a maximum amount of money and a minimum amount of money. Okay, the absolute lowest minimum was 900, and then the absolute max highest amount was 1,400. Okay, but we can identify these on the graph. They're pretty simple that way, but we got to use the table to prove it. So the relative minima are at x equals 9 or 6 and 9. So that's month 6 and month 9. Relative max are at month 5 and month 8. So those are the high points, comparing them to the surrounding points. Okay, and the balance in the account is the lowest at the minima. The balance of the account is the highest at the maxima. That's what it means in the context of the situation. Okay, so that's my lecture for you.